Here's a video that covers the very end of section 4 or 5. So if you think back to 4 or 5, what we talked about was integration with basic U substitution, trig integration with basic U substitution, and this is the third piece. How does U substitution work with something called complete U substitution, and then how do we deal with boundaries and definite integrals when we do U substitution? So this is the last piece of the notes. So what you'll notice when you look at this problem is it starts off looking just like regular U substitution. You have a composite function. The composite function is this x minus 3 under a radical. We let U equal the x minus 3, the piece that's having something done to it. When we take the derivative, we get just 1, or we write dx. And here's where the issue starts to come in. Normally when we have our du piece, any extra variables that are part of my piece that I'm trying to integrate are used up in the du. It's part of the du. What's special about this problem, and what's special about anything that needs a complete U substitution, is we have this extra variable piece. It's there, it has really no purpose as far as it's not part of u and it's not part of du. So what we have to do, our technique is kind of an algebra technique. We're going to completely substitute not just the u and the du, we're also going to have to take that x and figure out a way to replace it with u's. And it's going to come from this line right here. I know that u I called x minus 3. So if I do a little algebra manipulation and I add 3 to both sides, I know that u plus 3 is equal to x. So now when I start making my replacements, I am going to replace the x that's in the numerator with u plus 3. I'm going to replace the denominator with u being square rooted, so I'm going to write it in a better form. I'm going to write it as u to the 1/2. And I had no adjustment that had to be made. Sometimes you will have this adjustment. If you look right here, there is nothing here that I need to adjust, so it is perfect in that sense. When you do complete U substitution, not only will you have this extra variable that you have to replace, you're always going to have to do an extra algebra step. You're not ready to integrate at this point. Your extra algebra step is either going to be a distributing step or a pretzel step. It's going to just depend on the way it's set up. If you look at this one, this is a pretzel step. Whenever we look at this, we're going to take u divided by u to the 1/2. We get u to the 1/2. Plus 3 divided by u to the 1/2. We're going to write it as 3u to the negative 1/2. And you will always have that with the complete U substitution. You always have the extra variable, and you always have the extra algebra step. Now we integrate as usual, power 1 greater divided by that power. We're going to get 2/3 u to the 3/2, and then plus 3 times 2 u to the 1/2. Clean it up a little bit. I'm going to write it as 2/3. I'm going to put the u back in, so the u was x minus 3. So I'm going to put x minus 3 to the 3/2. Plus, I'm going to multiply the coefficients, giving me 6. And then we have x minus 3 to the 1/2 plus c. So that is what we call complete U substitution, because we have an extra variable piece that did not get taken up as far as u or as part as du, and we have the extra algebra to get it to be something that we're capable of integrating using our power rules. The other thing we talk about briefly in 4 or 5 is a type of problem that's really common on AP tests. They do a lot of this in multiple choice, where they ask you to rewrite a definite integral in terms of u. It's also a version of complete U substitution, but what's complete about this one is now we are not only making the adjustment, writing the u piece in, but we're also going to adjust the boundaries of integration. Most problems like this on an AP test are not problems that they actually want you to get a final answer. We don't want the numeric answer here. It's not asking you area or anything like that. It's just asking you to change the way that it's written. So we're going to start the problem the same way. We're going to start the problem by writing what u is. So u is going to be the x cubed minus 4. We're going to write down what du is and see if we need to make any adjustments. Du is 3x squared dx. We have the x squared. We don't need the 3, so we're going to divide that out, giving me a 1/3 adjustment. We are also going to write down what's being done to u. So u is being taken to the 2/3 power. And here's where the extra piece is different. It's usually the piece on an AP test that sometimes gets students, because our textbook does not do a very good job of explaining this. They a lot of times don't even talk about it, but it's talked about on an AP test. Whenever I look at my boundaries, the 1 and the 3, these are x boundaries because we are working with x's. If we switch to u's, then we need to make sure our boundaries are also u's. It's not difficult to switch, it's just a matter of remembering to switch. If x equals 1, that's my lower boundary, then all I have to do to figure out what u is plug in 1 wherever we have this equation of what u equals. So u equals 1 cubed minus 4, so u equals 1 minus 4, which is negative 3. That means my lower boundary, if I'm talking about u's, should be a negative 3, not a 1. So we're going to do the same thing with the upper boundary. The upper boundary is x equals 3. Well, I don't want to know x. I want to know what u is when x is 3. So I'm going to put a 3 here. I get 3 cubed minus 4, which is 27, minus 4, which is 23. And that is my upper boundary. Nice kind of trick when you're getting used to seeing these problems on an AP test is a lot of times one of your choices, one of your wrong choices, has the exact same boundaries. You know immediately when you look at your choices, if they didn't change the boundaries, then they didn't finish the problem. So if you look at a choice, if this was a multiple choice where you had A, B, C, D, if say letter A or letter B still had boundaries of 1 and 3, it can't be right because they didn't make that complete adjustment. So what you see in these two problems side by side are different ways to do what's called complete use substitution. The first one trying to find a way to rewrite that extra variable, and this one trying to find a way to change your boundaries so that everything is truly in use.